Hi guys, my name is Mr. Okin, and today we're going to introduce rate law and talk a little bit about carbon dating and how that is used to identify the age of different fossils that are found over the Earth. So I'm going to switch over to the document camera and we're going to take a couple of notes and then do some examples with equations that you'll be given with that. So our objective today, our objective is to understand rate law and the half-life formulas for the purpose of carbon dating. So why don't we jump right into that? Rate law, if you have the general equation AA plus BB turns into CC plus DD, then the rate equation for that from the rate that it takes from starting with your reactants to going to products is going to be K times A, concentration of A to some order of magnitude, times the concentration of B to some order of magnitude, where K is denoted as the rate constant. And depending on what order of magnitude we're using for this, it's going to have different units, ranging anywhere from molarities per second to, we're going to go up to molarity seconds, molarity times seconds. And that M and N are just going to, they're just what the order of each concentration is. So to find the total order of the equation and of the rate law, we're just going to add those two together. And the only way that we know now how to determine what M and N are to experiment. So these are determined by experiments. And then just another quick thing, most of the reactions that we are going to see and that we're going to cover will be either the 0th order, the 1st order, or the 2nd order. So starting to look at the 0th order, if we have a equation, if we have anything like that we have up here that we know is 0 order based on our data, meaning that for every increase in concentrations, nothing changes. So the only changes that help speed up the reaction are temperature and pressure. So any changes in concentration won't change how fast the reaction goes. That's a 0 order. So the rate is just equal to the rate constant, which has units of molarity per second. And then if we take a look at the integrated rate law for that, because we're looking at the rate laws, we're going to find that that is denoted as the concentration at any time t is equal to the opposite of the rate constant times time plus whatever the starting concentration was. And to solve for the half-life of this reaction, of any 0 order reaction, it's going to have the same equation to solve for the half-life. So we're just going to set that A of t that we have right here equal to the initial concentration divided by 2, because we want half of that. We're looking for how long it takes to go to half of your initial concentration. So if we say that that's A naught over 2 equals opposite KT plus our concentration, our initial concentration, A naught, we can solve for T by subtracting over, so this is the same thing as saying A naught over 1, right? Or 2A naught over 2. So we'll get KT is equal to A naught over 2, which means that our half-life, T1 half, is equal to A naught over 2K. Okay? So now we're going to move on to first order reactions. More paper. We're going to move on to first order reactions. Orient it this way. And we're going to say first order. So that's anything based on experimental value that the rate of the equation changes the same amount as the concentration. So if the concentration doubles, then the rate doubles, something like that. So that means that the rate is equal to the rate constant times your concentration to the first power, which is either the concentration of A or it can be the concentration of B. So we're just looking at the reactants. That makes our integrated rate law. There are actually three different ways you can write it. The first way is you can say that the natural log of the concentration at any set time is equal to the opposite of the rate constant times time plus the natural log of the starting concentration. You could isolate your KT, and you can say that the natural log of AT over your initial concentration is equal to the opposite of KT. And what I did there was knowing just a general law of how natural logs work. If you subtract them, it's the same thing as dividing them inside the natural log. So natural log of x minus natural log of y, I'm going to write that down, minus natural log of y is the same thing as writing the natural log of x divided by y. So that's all I did there. And then the third way, if you want to just isolate the concentrations by themselves, and it'll look a little bit like the first equation, like the zero order integrated rate law, I will say that the concentration at any point in time is equal to the initial concentration times e to the opposite, to the negative rate constant times time. So that means that our half-life, if I use the second equation, I'm going to do that one just out of simplicity's sake. You could do with either of them, you should get the same answer, and you're more than welcome to spend the time to do that. It will help you really learn these rate laws. I'm going to just plug in right away, so I'm going to say it's A naught over 2 instead of the concentration at any time. So I'm going to say it's the concentration of the half-life, so that's just the initial concentration over 2 divided by the initial concentration is equal to opposite of KT. And we're going to say that's the T of 1/2. So we know that those concentrations are going to cancel out. We're going to get the natural log of 1/2 is equal to opposite of K T 1/2. And just something for simplicity's sake, we know that the natural log of 1 is actually going to be 0. So if we do the natural log of 1/2, that's the same thing as saying the natural log of 1 minus the natural log of 2 equals, so that's the natural log of 1 minus the natural log of 2. So that's the same thing as saying 0 minus the natural log of 2. or the negative natural log of 2. So our t1 half, we're going to combine a couple steps here, is the natural log of 2 over k. We can say that they're both opposite, but those negatives will cancel each other out. And then finally moving on to second order equations. There are three different ways you can write the rate. The rate is either going to be k times a to the second, or rate equals k times b to the second, depending on your reactants, or your rate can equal k times a to the first times b to the first, because our total order we want to be second, so it's any of those two numbers, m plus n, that have to equal 2. So in this case, we have m is equal to 2 and n is equal to 0, which means that the concentration of B is 1, and you don't really have to write it in the equation. Or we can have it like this, where m and n both equal 1, and then when you add them together, you get 2. So moving on to the integrated rate law. That is going to be the inverse of the concentration, or 1 over the concentration at any point in time is equal to 1 over the concentration of the initial value plus your rate constant times time. And then the half-life from that. So if I just plug in what it means for the half-life, so it's going to be A naught over 2 equals 1 over concentration of A naught plus KT. Then when you subtract that over, you're going to, first, why don't we rearrange this? So if that 2 is on the bottom, we can actually pull it to the top, because we're saying it's just flipped. So we're going to say it's 2 over A naught minus 1 over A naught is equal to KT. So since they have the same denominators, we can just go ahead and subtract them. So we're just going to get 1 over A naught is equal to KT. And those are all the, well, it's not there, but these are all the half-lives times. So then our half-life is going to be 1 over K times A naught. So that is a second order reaction. These aren't going to be things you're going to need to memorize. It's nice to see the derivations of them, but they will be provided to you throughout the year whenever you need to use them. So we're going to move on now and talk about carbon dating. So, let me orient this right. Carbon dating. There are many ways to determine the age of something in science. Carbon dating is probably one of the more popular ones. Any sort of radioactive decay dating scheme that we're going to be using is going to be a first order reaction. So just going back to here, we're going to be looking at the top, so our half-life is that T1 half equals ln 2 over K. But carbon dating, like I said, it's considered a first order reaction. It's used to determine how old something is. And then just a couple of different constants you want to know when dealing with carbon dating. The half-life of the carbon we're looking at, which is carbon 14, as it decays to carbon 12, is around 5,700 years. So it's near 5,730 years long. So that's how long it takes for something that's completely made out of carbon, to deteriorate its carbon-14 to half of what it was originally. And then the K we're going to use, the rate constant, is going to be negative 0.693. So if we want to determine the age of a fossil, we're going to take that half-life equation. We're going to say that the age, the time that's how old it is going to be the natural log of the percent of carbon-14 that we have divided by our rate constant, K, times our half-life. So times the time it takes to deteriorate by 1/2. So an example of that is how old would a fossil be that has only 30% of carbon-14 in it. So that one's pretty simple. You kind of just plug it into the equation and compute an answer. So we're going to say that our age, how old it is going to be the natural log of 0.3. We want to make sure that when we're doing this, we're not actually using the 30% because that's going to change our natural log answer, and it's going to throw us off a little bit. So you want to make sure it's not in percent notation. It's going to be in decimal notation of percent, so anything from 0 to 1 instead of from 0 to 100. So you can just divide your percentage by 100, and that's going to be what number you plug in there. Divided by negative 0.693, and we're going to multiply that by 5730. And if we do that and we plug everything correctly, we're going to find out that the age of the fossil is just around 10,000 years old. So it's going to be something like that. That's basically how you use carbon dating and how you use half-lives to determine how old something is. Just for a little bit of homework before you come into class, I want you to tell me what percent of carbon-14 is in a fossil that is 24,000 years old. And I also want to know how old a fossil is that only has, let's go with 6.25% of carbon-14 in it, and how many half-lives is that? So, just a little hint with that one. The first part of that is like what the example is. You can kind of plug it in and figure that out. The second one, we didn't actually go over how many half-lives it is, or how many half-lives it is, but the way that the numbers work out, you can basically say, well, one half-life is 50%, so then you can kind of go down and count, if you increase one half-life, what does that do to the current percentage, and you can figure out what that means when it's 6.25%. So, do that for class, and bring that in tomorrow, and we'll go over that and other questions, and then start work on a lab that uses carbon dating. Okay, so that's all that's all that I have for you guys right now. So go out, um, copy down these notes, kind of look over them and see what makes sense, what doesn't, and kind of bring those questions to class and we can go over them a little bit more specifically. And then also bring those answers and we'll go over those before the lab. Thanks.